Our next speaker is Haobin, and he's going to talk about ASN1 Star, a provably correct non-malleable parsing for ASN1 DER.
Okay, so hi everyone. My name is Haobin. I'm come from Cornell University, and today I would like to present my work on formal verification of provably correct non-malleable parsing of AS1DR. And this is done with my wonderful collaborators from Microsoft Research Cambridge and Microsoft Research Redmond. Okay, so let's start by looking into what is ASN1. So ASN1 stands for Abstract Syntax Notation 1. It is a standardized data format description language since 1984. So you might wonder, why should you care about this since it's almost 40 years old? Because it is used everywhere in the most security critical data in communication. If you have ever used a browser, a modern browser, and have seen this little lock next to your address line, that means your browser has checked the identity of the server it is talking to by checking a thing called X59 certificate, which is defined in this AS1 data format language. Okay, so here is a simple example for the AS1 declaration. We have this full quotation, which is a tuple that contains the serial number field, which is an integer, and the code field, which is a ASCII string. And one thing you can do for this AS1 declaration is to come up with values that meets this declaration. For instance, here is a concrete value, full. The serial number field is set to 42, and the code is to be or not to be. So this is straightforward. And what is DR? DR stands for Distinguished Encoding Rules, and it is actually a set of translation rules between those high-level AS1 values and binary representations. For instance, the example I just gave, for foo, you can actually translate between this concrete value of foo and this binary representation of foo. But why DR? This is because DR is crucial to many security applications. It is designed to satisfy two properties. One is the unambiguity, and the other one is non-malleability. So unambiguity here means that given any binary representation, it can only be parsed into a single value, or the parsing will fail because it doesn't correspond to any value. And this is obviously necessary for the thing to be parsable. And what about non-malleability? Non-malleability, and here I like to specify that in parsing domain, this means like modifying any part of the binary string in any way will result in the parsing giving you a different value from the original string or end up failing. So this is actually quite important for our goal of security, because if you use any kind of cryptographic scheme, such as signature or hashes, you can only apply those operations on the binary representation of the values instead of on the values themselves. And here is a famous example that exploits a buggy parser for AS1DR, because that buggy parser doesn't give you the malleability. And this is actually quite a challenging problem, because there are so many tricky cases that can trip you in the actual implementation. Here are some very recent high severity CVE bugs that are related to just the AS1 parsing in OpenSSL. So you can see this is far from solve the problem, and only if we had the certified and proven parsers at our command. So here comes our work. We claim to be the first formalization of AS1DR, and our main theorem states that all well-formed AS1 declarations will induce non-malleable parsers. And we believe that this provides us a basis for understanding this long-standing standard, which were described in natural language. And then we also have done some experimental evaluation of the extracted parser on practical formats. Okay, so here comes the high-level idea of our work, which is very similar to the previous lines of work in parsing. So you come up with some domain-specific data format language. You build a verified compiler, and then you can extract the provably correct parsers for free. And then the good thing about this structure is that you only need to build your compiler once for all, and then the user only need to write new data formats in the domain-specific language you described for any kinds of new formats they want to use. And this is exactly the pattern we followed. So we formalized AS1 as this domain-specific language we call AS1 Star. And then we built our compiler, which is the as parser interpreter. And then we extracted the output of the compiler into OCaml, and then we did some empirical evaluation on the extracted parser. And here I would like to stress that the goal of our empirical evaluation is that we want to make sure that formalization corresponds to the actual usage of this data format in practice. So far, we cannot give you a high-performance substitute of the ASN.1 parsers in usage. And that is some interesting future work for us. And of course, the whole development is in the F-star proof assistant on top of the EverParse parsing combinator library. Okay, so that's the end of the talk. No, because that's not as easy as it seems. So here comes the actual challenges comparing to previous work. So the first thing is that we don't have complete freedom in our choice of design of this data format language. So we must comply with the existing usage of AS1 in the actual standard, the RFCs. To make matters worse, the RFCs is not only using the AS1 standard syntax, but they also use natural language to describe the actual data format they want. And in this formalization world, we would also like AS1 Star to capture those constraints as well. And to make matters even worse, this is complicated by the huge quantity of existing RFCs. Okay, so what are our plans? So since this is the compiler section, I suppose we are all familiar with this idea of slaying the dragon of complexity of compiler design. And we have two weapons. The first weapon is the right abstractions, and the second is the dependent types, and also the interns. We have three weapons, the right abstractions, the dependent types, and the interns. Okay. So now for something completely relevant. How do we actually use our three weapons? So let's dive into this little box that's formalized in F-star. Okay, so let's consider our world divided into the informal land of the RFCs and the formal land in F-star. And in between them, there are nice abstractions that bridges those two lands. So as the example I gave earlier, you have AS1 declarations, and then it's very natural to model them as syntax trees, and this is exactly what we do in ASN1. Here we have the declaration type that corresponds to the pure syntactic object of those declarations. And of course, the declaration would give you some set of values, and the abstraction for those set of values are just simple data types. And in our development, this gives the first semantics to our syntax, which we call the as type semantics. Here, as an example, we can see that in AS1 Star, you can translate this declaration of full quotation into that of a type, which here gives you a pair of an integer and the ASCII string. And here we have the first semantics, the AS1 as type. So what about DR? So in the informal land, if you think about it, DR basically gives you a bunch of binary strings that has some relationship between the set of values that's induced by the AS1 declaration. And here, our proposal to the abstraction is that we model them as sets of bytes, but with the additional constraint that those should be isomorphic to the type given by the as type semantics. So here is our definition for the as parser semantics. So as you can see, given a declaration, it gives you back a parser. And this is where we use our second weapon, which is the dependent type, because the return type of the parser is dependent on the output of the as type semantics, which takes this argument D, that is the declaration. So if we unfold the definition of the AS1 strong parser type further, we'll see that it actually used the existing definitions of parsers in everparse. And further down, we say it unfolds into a function that projects binary strings into the corresponding type or none, plus a bunch of restrictions on the behavior of the function to make it a parser. So I just want to stress that the red box, the AS1 as parser, is exactly the main result of this work. So our construction of the AS1 as parser actually proves that all well-formed declarations will give you non-malleable parsers, because in the AS1 strong parser, we enforce those parsers to be non-malleable. And this is the high-level idea of this work in a single slide. Okay, so now I'm going to dive into some of the details in our development. So let's start with the syntax. On the right, you can see this is the transcribed AS1 star declaration. And then on the left, you can see the to-be-signed X59 certificate, which is the actual declaration taken from the RFC document. So those two syntax are quite similar to each other, and I will ignore further details. So for our first semantics, the as-type semantics, very unsurprisingly, we implemented as an interpreter. And here you can see that it's basically doing a type match on the syntax tree described by the declaration value. And to make this interpreter work, you basically need two kinds of materials. The first kind of materials handles the terminal cases. And here is an example, which is the printable string in ASN1. So the way we define printable string here is that it's a list of bytes where each byte is a refinement type. It's the basic byte type refined by this proposition that says the byte contains a character that is actually printable. The second kind of things you need are the combinators. And here we implement those mostly as type constructors, such as pairs, tuples, and so on. So for our second semantics that translates AS1 star declarations to parsers, we also implement those as interpreters. And it follows very similar structure as type semantics, but with some more details. So although this is defined as an interpreter, it actually works as a compiler because we can do partial evaluation on a specific declaration given. And for this interpreter to work, you need to build a bunch of new parsers and parser combinators. And here I'd like to highlight one of them, which we call the automaton parser combinator that works very well for parsers based on state machines. So in our development of AS1 star, we found that many parsers for the AS1 data types often have this logic that can be easily described by some kind of state machine. However, the challenge in building formal verified version of those parsers, we found that usually they comes two kinds of problem. First kind of problem is that you have to handle the low-level detail of parsing when you are doing this high-level computation following this state machine diagram. As you can see, for this state machine, there are many ways you can fail from each of those states. And the reason for that is the low-level parsing actions can fail in many different ways. The second problem is that improving the correctness of this parser, you have to do some kind of global induction on the structure or on the traces of this specific state machine. And we find that to be quite complex. So our solution to this problem is that we build this generic automata combinator that can work for an abstract description of the state machine. So here is an example. So you plug in some high-level description of your state machine without mentioning the low-level parser details, and you plug in some parser for the alphabet of your state machine, which is verified elsewhere. And then you only need to prove some local properties on this high-level representation of your state machine. And then magically, the automata combinator will figure out the global induction for you, and you get your nice parser right out of the box. More details can be found in our paper. So lastly, I would like to explain a little bit on our evaluation. So the goal of our evaluation is to answer this question. Does our formalization of AS1DR matches what is actually in use in practice? So the only way to check that is to connect it back to the actual data that's in use. So here is our workflow. So we started with all the RFCs, and someone manually transcribed those data formats into the AS1 star declarations. And we use our AsParser compiler to compile those into parsers, and then we extract them to OCaml. And we perform our experiments on the extracted parsers. So here is the workflow of our experiments. First, we collect some kind of data set in binary. We plug in those data values into our parser, which tell us whether it accepts the value or rejects the value. And it only checks the syntactic properties because it's a parser. And then for some of those cases, we do manual inspection of the output of the parser and the input to make sure that our parser is doing the right thing. So due to time constraints, I'm only going to explain our results on the X509 certificate data format. So here is the first data set, which is the EFF data set. EFF stands for Electronic Frontier Foundation, and this data set contains 11 million certificates collected from the wild back in 2010. And since those certificates live in the wild, we would expect that most of them should be syntactically valid. But this is actually not the case. As you can see in this first row, that there are about 7% of them rejected by our parsers. So to investigate this, we randomly selected a subset based on IP addresses. So in the subset of 10,000 certificates, we manually inspect the ones rejected by our parser, and then we confirm that all those 10% certificates actually contain syntactic errors. It is a little bit horrifying to know that 10% of the certificates that are in use already fails the parsing step. And then another data set is the OpenSSL data set, which contains about 2,000 certificates. And this data set is generated by OpenSSL fuzzers. So you can expect that most of them should be incorrect because they are basically generated randomly. So we manually inspected the ones we accept, and we confirmed that the ones we accept actually contain no syntactic errors. Perhaps they are mutated from some valid certificates, and the part it mutated did not change the syntactic property of those parsers. So in conclusion, we believe we are the first formalization of AS1DR, which is an important data format in practice. And our main theorem proves that well-formed AS1 declarations would induce non-malleable parsers. We think that we continue to explore this frontier of practical formal verification through designing domain-specific language for this parsing domain. And of course, there are many future steps for us to take in order for this work to have more practical impact. This includes efficient low-level parsers and serializers. It also includes connecting to more semantic validation after we have verified the syntactic properties of the inputs. Okay, So this is a picture of me trying to read all the RFC documents, and thank you for your attention.
We have time for a couple questions. Adam?
I don't know if I missed it in the discussion of the experimental evaluation, but did you have any tests where you made sure that the right actual content was being parsed out of these messages, rather than just whether you got this Boolean thumbs up or thumbs down?
So we didn't test all of those values, but we have some simple checks that checks part of those values.
Okay, thanks.
So to add a little bit on that, we actually did an analysis of what kind of errors we reject. And here you can see that our parser, we can actually tell you what kind of error are inside those certificates. So we did validate some parts of the fields we actually parsed.
I was wondering about those like 10% of certificates that your parser rejected. Have you checked what other parsers do with them? Like if you give them to OpenSSL or Firefox or something?
So we didn't directly check that. But I can tell you that from the EFF dataset, when they collected the dataset, they actually went all the parsers through the OpenSSL AS1 parser at that time. And it's only the certificate that can pass that check can be included in this dataset.
So there's a discrepancy here between your parser and the OpenSSL parser?
Yeah, but that's an old version of OpenSSL, and it didn't enforce the full properties we enforce here because it's using a different ASN declaration that's not capturing everything said in the RFCs.
Okay, isn't that a problem?
That might be a problem for 2010, but I don't know what is the situation currently.
So I have a related question. This 10% of certificates that basically should do parse in practice. I'm a little confused. Does this indicate errors in the parser? Is it an error? Like, does it lead to security errors if you parse too many programs, or is this just things have changed and those things should no longer parse?
So
Since the data set was
yeah,
created?
I think I understand your question correctly. So I think there are three cases. So for one case is that things have changed since then. The other case is that it depends on what kind of specification you use when you do the parsing. I can give you a further example. So here, if you look at the default role, there are actually a few very extreme corner cases about the default role in DER, which enforces this whole thing to be non-malleable. A parser does have not to fully comply with the DR standard for it to work with most of the certificates that's available online. So at that time, I don't think you have a very expressive language that can capture this kind of constraints, such as defaults or extensions. So usually the parsing at that time was done in multiple steps, and some of the checks go into the later steps after the first pass of the parsing that follows a more generic AS1 declaration that doesn't contain all those details. So I think that's another thing. And the third thing is, well, bad news. There are some certificates that are just bad. For instance, if you look at the case in terminals, you can see that by definition, printable does not contain asterisks and @ symbols, but some people put their email address in a field that's a printable string, and that's strictly exactly the syntactic error we catch.
I have other questions, and I'm sure you have questions, but we better stop it there and take the rest of you again.